All right. I will now move on to proof. So there are three parts in the proof. The first is for the proof. I will use the union bound again and use the random coding argument so that we can do the proof with the assumption of sending the first code word selected randomly, and then use the argument of joint typicality. And we'll use the Farnose inequality to do the converse proof. The only part that is added to the forward and converse proof materials in chapter 7 is the power constraint. So that's the only argument. So except that second and third are exactly the same as chapter 7. So just be careful with the power, convergence in power argument. Then we will be able to understand second and third item easily. Okay, and the new part here is the first one here, capacity based on sphere packing argument. So this is the part that is new. So I will talk about that. So set up for sphere packing argument. So we will prove the capacity with this very interesting idea. The idea is based on a surface hardening that we covered in our previous lectures. So here a code is n tuple vectors, that's x1, xn, where each xi is a sample of a real valued Gaussian with a zero mean and radius p. Okay, so the size of the code is the number of code words, which is 2 to the power of nc, where c is the rate of the code. So I will use c for sphere packing argument to be the rate. Okay, so via each code word, which we send k bits, where k is n times c. And we use vectors in this particular set of node as boldface letters. So y, which is the received signal vector using channel n times, is equal to xi, where I is the index for the code word. Okay, so I runs from 1 to all the way up to 2nc. And then additive noise vector z, which is Gaussian, is added to xi, and that's what you receive. So the notation is not very clean and nice. So I here use this subscript as index for a symbol element within a code word. But when I use a boldface, I use the subscript to describe the index of the code word. But if we have too many notations, it is difficult to read. So you just need to, be aware of these things. Okay. So where y, xi, z are n tuple vectors. Okay. So here, since there are vectors, the average energy of the code word xi is n times p, right? Where p is expected value of each element, right? So each element. So p is expected value of xi square. So that's energy of the code word xi, right? That's the energy of the code word xi. So if you have x1, for example, where let's say you have 10 elements, right? And each one is IID, Gaussian with mean 0 power p, then basically the energy of this whole thing is n times p. Okay, and if we take the square root of this thing, then basically that's the standard deviation, right? Or the length of the vector. So this is the length of the vector x. So in my hand writing, I'll use underbar to denote vector. Okay, so xi underbar to denote. Okay, so it is going to be the length, okay, of the vector xi. Okay, and same way I can describe the energy of the noise is n times capital N. Energy of the received signal y is n times p plus n, and so on. Okay, so if we take the square root of each one, let's say that is going to be the length of the vector x, length of vector z, length of vector y. So if you take the square root of the energy, that is the length of vector. Okay, so in the we can talk about n-dimensional vector space, right? So we can talk about the origin of this vector space, and when you have a vector x, let's say x1, first code word vector, it has an element x11, x12, or x1 using the notation that we've been using. Okay, x1, I'm sorry, 2 x n 1, using the notation that we've been using. So this could be a code word, and the length of this vector, which is norm of the L2 norm. L2 norm of this vector is length of vector x1. So that's the geometrical interpretation of code word in the n-dimensional vector space. Okay, so once you have that, then we can talk about now. So that's the length of the vector. Okay, and then we can talk about y. So y can also be described as y is x1 plus noise vector z, right? And that's vector addition. And then when you do the vector addition, this is your vector y, where that is x1 plus z. Right. So this is your vector in the n-dimensional vector space. Right. So this is a y vector. This is the noise vector. Right. So if you send x1, you will receive y somewhere around this surface of a sphere. Surface hardening occurs. So you give a little bit and take away a little bit. That is the square root of n times. So the radius of this one is n times n. And so you take plus or minus epsilon, right? So that's the radius, which is the square root of n times n. And then if you give a epsilon, you will talk about this outer region, and take away epsilon, you will talk about the inner region. So when you send x1, you will receive y, which belongs to this region, okay? The surface of this sphere, n-dimensional sphere, with a probability close to 1, okay? You will receive y inside this inner circle or outside of this inner circle as well, outside of the outer circle as well. So in and out, the collection of all those, vectors of y outside of this region. So collection of all these guys outside of this region, right? So that is the whole vector space. Maybe we can say that the sample space of y, and take away the typical set, which is described by this surface. Typical set, right? Typical set. So y belongs to this, inside or outside. So that is, we can say, we can define it as atypical set, epsilon and C. So so we need to define this as the atypical set. So y belongs to atypical set. Probability of such event goes down to 0 as n goes to infinity. What probability of y belongs to the typical set, which is described by this surface, converges to 1 as n goes to infinity. Either that, both. This occurs and this also occurs. The same. This is the same thing. Okay. So that's convergence in probability. So if we describe code word in vector space, noise in the vector space, and received symbol in the vector space, energy and length of the vector, these type of geometrical explanation and interpretation can be utilized in the proof of capacity. Okay, now let's move on. So derivation of channel capacity based on sphere packing argument. Basically, we use k bits to make the code book, and you send the n-tuple vector over the channel, n-tuple vector output, and then you make a decision, and then there are k bits. Okay, so you have encoding, decoding, but since we use random code book, all we had to do is to make sure that as you increase n, you need to show the existence of a code book that we can make the probability of decision error, the decoding error, very small as you increase n. So the arguments that, the geometrical explanation that we have given in a previous page can be utilized for this proof. Okay, so we are interested in showing that it is possible to find. So we just need to show the existence, right? Achievability, existence. So the channel coding theorem is existential proof. Okay. Later on in the channel coding theory class, we can talk about how to uh, make such a code exactly will be discussed, but in this particular, in the information theory, we just need to show the existence, okay, of such a code. So we are interested in showing it is possible to find a code with RACI with the probability of making decision errors at the receiver approaches zero as n grows to infinity. That's what we need to show. And then here we will talk about maximum decision likely rule. Maximum likelihood decision rule. So for find ith code word whose Euclidean distance with the received symbol, received vector y is the minimum, and the decode for I. So if you have received this signal symbol vector y, and then you compare with the other code word, and you find the one that has a minimum distance, right? Then basically, why do we have to use a maximum likelihood rule? Basically, that is based on this, right? So for example, let's say you can consider likelihood function, right? Then basically, this is the the distribution is what? So we have that relation is given like this, right? In previous page, and the exponent we have a minus, in this case, xi minus y, sorry. Select the eraser, so let's minus xi, and okay, so that's the PDF. That's the likelihood function. So this is the likelihood function, right? And that's the likelihood function. And then we want to maximize, find the I that has the maximum likelihood function, right? Then this part is the same, so we can ignore it. So that can be shown that maximum likelihood function is the minimum distance between the two, okay? And then k here, we assume that it is a wide, IID, and this is the n times identity matrix, right? So this part right here becomes y minus xi L to norm square. Okay, so that becomes maximum becomes minimum because we have a minus sign here. So if the exponent is small, I forgot to divide by 2. If exponent is small, then the probability is large. Okay, or the likelihood function is the greater. Okay, so that is the minimum of our index I. So we can make R or NC in this case, and the minimum distance y. I'm sorry, y. Y. I don't need index I for y, right? And minus xi L to me. Okay, so maximum likelihood decision. So this is the decision I. So maximum likelihood decision is, in the case of additive white Gaussian noise, is minimum of Euclidean distance. So you compare with every possible transmit vector xi's, compare with the and distance from y, and then make the decision where you have a smallest distance from y. Okay, so that's the maximum likelihood decision rule. So it becomes a minimum distance rule. And then we can talk about the surface hardening. If you send xi, you will receive y somewhere in these regions. So those y's are typical when you send xi. All the y's which is inside this sphere or outside are not typical. So probability of not typical output goes to 0, but probability of typical output, which you find your received vector y inside this surface, goes to the probability of such event converges to 1 as you increase n. So that's the argument, right? Surface hardening. And if you want have the minimum distance rule applied, so basically you will consider another code word. Let's say consider 2 code words possible. So for example, x1 you send, you fix x1 to be this code word. So the x1 vector is right here, and then you know the noise power, so you can draw the surface of this sphere, and then suppose that you have chosen vector x2 whose surface does not overlap with the sphere of the first code word. So as long as you have 2 surfaces not overlapping with each other, then the confusion between the 2 code words is going to be very small, right? Converging to 0 as you increase n, right? So you can select code word enough apart from with each other, and if you continue to build these spheres, right, and at the center you assign the code word, right, x3, x4. As long as you can have these spheres do not overlap with each other, and basically that will give you code book, right, with the probability of error converging to 0. Okay, so that's the sphere packing argument. Okay, so pack as many noise spheres as possible inside the receiver space. So what is the receiver space? Receiver space is from the origin has a radius ry, where radius of the vector y is square root of n times of p plus n, right? In the setup, right? We have done that. And then we can define the volume of this space. And then within this space of received signal, so these are the typical sets, right? For the noise, the received vector y. And then basically we can talk about how many small spheres can be packed inside the whole receiver space. Typical set of the receiver space, typical set of the receive vector. Okay, all right. So the capacity argument, capacity obtained from the sphere packing argument is this. So note that as long as we have the right number of code words in a code, such that the noise sphere does not overlap with each other, then PE kept very small, can be kept very small. Then the question is, how many noise spheres can be packed inside the volume of the received signal Y? So there is a symbol mistake, typo here. So Y. The volume of n-dimensional sphere of radius Q is AN times QN, where Q is the radius. Okay. So here, for example, let's say pi r square is the A2. So that is the area. So in this particular case, pi is the A2, okay? And A3 is 4/3, right? Because the volume of a sphere is what? So this is area. Area of a two-dimensional sphere is pi r square, right? So the coefficient A2 is pi, and volume, three-dimensional sphere, volume of three-dimensional sphere is 4/3 pi r third, right? Okay, third power. So that's the 4 pi over 3. 4 pi over 3. So we can talk about this coefficient an, and then radius in this note is q to the power of n. So that's the volume of n-dimensional sphere of radius q. Radius q we can calculate. The radius of the received signal space is this, as we have done. The radius of the smaller sphere, which is noise sphere, is this. Then the capacity is the maximum number of noise spheres that can be packed inside the sphere of the received signal. So we just need to divide the volume of received signal sphere divided by the volume of the noise sphere. That gives you the maximum number of noise spheres, and that will also be equal to the maximum number of code words that are not confused with each other. Okay, so that's the last part. So number of noise spheres in the receiver signal space is the volume of the received signal sphere, which is this. Okay, here is the radius, and then noise sphere radius given right here, right here. So that's the volume of the noise sphere, volume of the received signal. So AN cancels out with each other, and this becomes P over N, which is signal to noise ratio +1 because of that, and taken to the power of N over 2. Thus, the capacity is the log, is the log 2 of number of code words, which is the size of the message set, will give you this, okay? And then if you divide this by n, that will give you per symbol used capacity. Okay, so that's the proof of capacity of AWGN channel using the sphere packing argument. So here is the sphere packing argument. You have radius of y, and this is radius of the signal. Okay, so when you talk about the typical set of y, it would be probably mostly located in the surface as well. And then in this surface, you have many noise spheres that will give you the number of code words. And the collection of all such, distinguishable noise spheres gives you the set of code words. So you can select the center of each noise sphere as the code word vector. Then you can prove the existence of n-dimensional code word set, whose probability of error goes to 0 as n increases. Okay, so that's the sphere packing argument based capacitive proof. I will talk about forward proof and converse in the next lecture.